Good day, students. Welcome to mathgotserved.com, where we don't just solve, we teach. In this clip, we're going over problems 16 to 20 of the January 2019 Algebra 1 New York Regents exam. For the entire collection, look to the description below, and do not forget to subscribe to our channel for updates to the remainder of this review series. Alright, let's take a look at question 16. In question 16, we are going to be comparing linear and exponential growth functions. Both functions will be presented in tabular format, and we are going to generate terms using the table and their respective formulas, and basically see which one has a higher value after a certain period of time. Okay, so the question reads, the table below shows the weight of Liam's pumpkin L of W and Patricius' pumpkin P of W over a 4-week period, where W represents the number of weeks. Liam's pumpkin grows at a constant rate. Patricius' pumpkin grows at a weekly rate of approximately 52%. Question: assuming the pumpkins grow at these rates through week 13, when comparing the weights of both Liam's and Patricia's pumpkins in week 10 and week 13, which statement is true? So basically what we just have to do is figure out the weight of Liam and Patricia's pumpkin in weeks 10 and week 13. Okay, and then we're going to know what the answer is. Alright, so we are told that Liam's pumpkin grows at a constant rate. Okay, so what does that tell us? If a function has a constant growth rate, what does that mean? Well, certain things that you want to note concerning growth rates. If you have a constant growth rate, that indicates that you add a difference over and over again. You're going to be adding the difference repeatedly. Alright, and in this scenario, what you have is a linear function. Linear functions have constant average rate of change, or constant rate of change, or constant growth rates. Now, in the case of Patricia's pumpkin, we have a growth rate of approximately 52%. Now, when you have a percentage growth rate, in this case, what you do, instead of add, you multiply. Okay, so you multiply by what? You multiply by 1 plus the percentage growth rate. And in this scenario, we have an exponential growth scenario. Okay, exponential growth function. Alright, so when you have a constant rate, is a linear function, just like a straight line. And then for the second one, if you have a percentage growth rate, is an exponential function, which is a function whose rate of change increases over time. Okay, alright, so with those two in mind, let's see if we can generate formulas for Liam's and Patricia's pumpkin. Okay, so for Liam's pumpkin, we want to see what L of W looks like. So for Liam, we have L of W. So since for L of W we have a constant rate, what are we going to do every single time? Well, we have to determine what the growth rate is. So from 2.4 to the constant difference, from 2.4 to 5.5, if you do the calculations, 5.5 minus 2.4 is 3.1. So you add 3.1. And then just to test it, if you add 3.1 to 5.5, guess what? You get 8.6. If you add the constant rate, which is 3.1, to 8.6, you get 11.6. Okay, so for the function L of W, what you do every time for the constant rate is you add the difference, which is what? 3.1. So add 3.1 every time. Alright, is an additive relationship. Now for Patricia's scenario, we have a constant growth rate. Okay, we have a variable growth rate. The variable growth rate is 52%. Okay, the percentage growth rate is 52%. So what does that tell us? For Patricia's weight function, we have a 52% growth rate. So what does that mean? That means that we're going to multiply by what? Multiply by 1.52 every time. Now, how did that happen? Well, 52% in decimal form is 0.52. You move the decimal point to the left 2 places, because when you're converting from percentage to decimal, you divide by 100. So move the decimal point to the right 2 places. Alright, so this is a percent growth rate, but since it's a growth rate, you're going to add 1, just like exponential functions, exponential growth models. You add 1 to that. That is why I came up with 1.52. So you multiply 1.52 every time. Now, something you want to note is that it's an approximate growth rate. Alright, so some rounding will be done in the determination of the weight in pounds for Patricia's pumpkin. So let's see if this is the case. Since we're multiplying decimals here, it's more effective for us to use a calculator. So what we're claiming is that what's happening is we're multiplying by what? We are multiplying by 1.52 every time. Okay, so from here to here, you multiply by 1.52, 1 plus a percentage growth rate, and then you repeat the same process over and over again. So let's test it just to make sure it's correct before we move on to determining what week 10 and 13 are. So 2.5 times 1.52 is 3.8. Bam. And then the next one, 3.8 times 1.52 is 5.776. So you see how they rounded it up to the 10th place. Okay, so they rounded up to 10th place, which is 5.8. So we go 5.8 times 1.52, and we get 8.81, rounded again. So we can see that what's happening here is we're multiplying by 1.52 repeatedly, and that's what an exponential function is all about. You constantly multiply by that growth rate. Alright, so to get week 10, what are we going to do? To get week 10, all we are simply going to do is add 3.1 to 11.7. Alright, that's not difficult to do. We just add 3.1 to 11.7, we get 14.8. And then how do we get week 10 for Patricia's pumpkin? Follow the same pattern. Multiply by that common ratio, which is 1.52. So multiply by 1.52, and let's see what that answer is. So we have 8.8 times 1.52, and we're going to round to the first decimal place, or the 10th place. Alright, multiply, we have 13.376. If we round up, that's going to be 13.4. Alright, so it's going to be 13.4. Now we can make a comparison here. Which one weighs more? We can see that Liam's pumpkin weighs more at week 10. Now, since the linear function has the lead, does that automatically mean that Liam's weight will remain the greater? Well, let's see. Let's take a look at what happens at week 11, 12, and 13. And when we get to 13, we're going to compare again. Okay? So all we're just going to be doing here is just for Liam's function, it's easy. We're just going to keep adding 3.1. So we add 3.1. And then we get for week 11, we get, what do we get? 17.9. And then we add another 3.1. For week 12, we're going to have 21. And then for 13, the last one, you add another 3.1. And then you have, let's see, 24.1. Alright, so that's that for Liam's weight. Now let's take a look at what the situation is with Patricia's pumpkin's weight. Okay, so what we're going to do, we're going to repeatedly multiply by 1.52. Okay, so multiply by 1.52 to get the weight for week 11, 12, and 13. Let me put a line there so that we can see what's going on. So this is for week 10, and this is week 11, and this is week 12, and then we're going to separate them from left to right. Okay, now let's do it. We're going to use a calculator here since we're multiplying. We rounded it up, so 13.4 times that common ratio, which is 1.52. Enter. We have 20.4. So 20.4. Oh, look at this. The exponential function has already exceeded the linear function. Now that shouldn't come as a surprise because a linear function has a constant growth rate, whereas an increasing exponential function has an increasing growth rate. So if you have an increasing exponential function and a linear function compared with each other, at a certain point in time, the exponential function is going to catch up and exceed the linear function. But the question is, when will that happen? Okay, so we can see that the exponential function has taken over, and guess what? The exponential function will maintain the lead because it is a function with an increasing growth rate, whereas the linear function has a constant growth rate. Okay, so let's see. 20.4, we're going to multiply that by the growth factor 1.52, and that gives us 31, just 31 as a whole. See, the lead is widening now. And then lastly, we're going to multiply 31 by 1.52 to get what the weight is in week 13. Alright, so we're just repeatedly multiplying by 1.52. Alright, we already know that the exponential function will win, but let me just show you. So 31 times 1.52. Let's do that again. 31 times 1.52. And your answer is 47.1. Wow, you see who the winner is? It's the exponential function. Alright. Okay, so let's see what's the correct answer. Liam's pumpkin will weigh more in week 10 and 13. The answer is that's wrong because Patricia weighs more in week 13 and Liam weighs more in week 10. Alright, so Patricia will weigh more in both weeks. No. Option 3, Liam's pumpkin will weigh more in week 10 and Patricia's pumpkin will weigh more in week 13. Absolutely, that's what's happening here. The answer to question number 16 is option 3, illustrating the comparison between the growth of linear and exponential functions. Alrighty, let's take a look at question 17. In question 17, we're going to be learning how to find the domain and range of a function graphically. Okay, alright, question 17 says the function f of x is graphed below. So this looks like part of an absolute value function. Okay, why do we say it's part of an absolute value function? It is part of an absolute value function because we know that the absolute function increases forever to the left and to the right. But in this particular function, it stops short in the left end. Okay, it stops right there. So it doesn't increase forever to the left. Okay, so it's a portion of an absolute value function, not a complete absolute value function. Alright, the question is, the domain of this function is... So what is the domain of this function? Before we do that, there's something you want to remember, which is basically what the domain and the range mean graphically. Okay, so recall, this is concerning domain and range. The domain is what? The domain is the width or horizontal span of your graph. Alright, how far to the left does the graph cover and how far to the right does the graph cover if it is projected down to the x-axis? Okay? And then the range represents what? Guess what it is? The range represents the height or the vertical span. How high can you go and how low can you go? Alright? How high can you go, how low can you go if the graph is projected on the y-axis? Okay, so if you think about projection, think about shadows. Okay, if a shadow is cast on the ground or on the wall, how wide is the shadow or how tall is the shadow? That's basically what we are talking about here. In this particular problem, we're asked to find the domain. So let's go ahead and figure what that is, and then I will show you what the range is so you can see the difference between both of them. Let's make our arrow pretty thin. Okay, so for the domain, what we're going to do is we're going to project this graph onto the x-axis. So what does that mean? You go straight down from the starting point, straight down, a line perpendicular to the x-axis. That's a straight down projection. And then this one will be projected straight down too. Alright, so how do these projections come about? Now imagine that there's a flashlight, a big powerful flashlight up here, flashing a light on this function. Okay, the shadow that this function casts on the x-axis or the floor is basically what the domain is. Alright, so that's the shadow is going to be right here. So we have, what are we going to have? This left point is a closed circle, so it's going to project a closed circle here. So starting from this point, whatever that is, that's -1. Starting from this point, is going to span everything in between all the way. Now this end right here is an arrow. Do you know what that means? It means that it keeps on going forever. So the projection will be an arrow also. Okay, so this point is projected as a point. This line right here is this entire interval. And then this arrow basically means that the projection will continue forever. No matter how far you go to the right, you will have a shadow being cast because the function keeps on going. Okay? Alright, so if you take a look at this weird number line we just drew, going from what? -1 all the way to infinity, that is the domain of our function. Okay? So if we want to write this down in interval notation, it's going to be from -1 to infinity. But if we want to write it using inequality notation, it's going to be x is what? X starts from -1 and goes on to infinity. So x is greater than, and since it's a closed circle, equal to -1. Alright? So our answer for question number 17 is option number 4. Alright, now this problem doesn't ask for range, but we might as well figure it out anyway, because on the next Regents exam you might be asked to find what the range is. So what is the range of this function? Do you see what the range is? Now since we have the portion of the function to the left and right, we're going to have to use two flashlights. We're going to need a flashlight to the left and a flashlight to the right, and then we're going to unite the two shadows that we get. Alright, so from the left side, this one gets projected on here as a point, and then from the right side, this gets projected to the top as an arrow. Okay, but since this is above, it has a line here, so we're going to have so let me draw my arrow properly. It's looking weird. Alright, so there goes my arrow right there. Draw it again. So we have an arrow going up. Okay. Alright, so from the left side is this point going all the way down. So this V, this vertex right here, is projected as a point on the y-axis. Okay. So from the left side we have this point and everything beneath, bam, 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 all the way to 0. But from the right we have this arrow, and guess what? Everything beneath. Okay, so basically extends the domain. So the domain basically the range basically starts from 0, and guess what? It goes up forever. Okay, up and up all the way to infinity. So what's the range going to be in this particular case? The range, which goes with the y, the range or the vertical span is going to go from 0 to infinity using interval notation, or using inequality notation, is going to be y is greater than or equal to 0. So if you look at this distractor here, number 3, that's terrible because it has x. When you're dealing with the range, you use y, or you can write f of x is greater than or equal to 0. So the notation alone can automatically help you to determine which is applicable. Alright, so this is the range from 0 to infinity, or y greater than 0 or equal to 0, and the domain is -1 to infinity, or x is greater than or equal to -1. Alright, let's take a look at question number 18. It reads, which pair of equations will have -1, 2 as a solution? Alright, so before we start this problem, let's go over what that term solution to an equation means. Okay, so something to note concerning solutions to an equation that has two variables. So this is what you want to keep in mind, and it is that an ordered pair so xy representing two numbers is a solution. What we're asked to find in this problem is a solution to to an equation, is a solution to an equation if what? If it makes the equation true, if it makes the equation true upon substitution. Okay, so when you substitute those values into the equation and you end up with a true statement, then it's a solution. All right, so another way to say that an ordered pair is a solution is to say, does that ordered pair satisfy the equation? So it satisfies it. Satisfying an equation basically means that when you plug in the variables, the solution into the equation, you end up with a true statement. Okay. Alright, so let's start with option 1. So option 1, we have two functions to be satisfied here. Y equals x plus 3 and y equals 2 to the x. Okay, so what we're going to be doing is we're going to plug in this ordered pair -1, 2 and see if we end up with a true statement. So the solution we are testing is -1, 2 for both equations. Okay, so we're going to be subbing here. X, this one is going to go into that spot, and then the 2 is going to go into the y spot right there. Same here, the 2 is going to go to that one, and then the -1 is going to go to the x. We're going to substitute. Okay, so let's do it. So for the first one, the question is 2 equal to, is it equal to -1 plus 3? Is it? Is 2 equal to -1 plus 3 is 2? Is 2 equal to 2? Yes. That's good. So it satisfies the first one. How about the second one? And we substitute. The question is 2 equal to 2 to the -1? Is it? What is 2 to the -1? We use the reciprocal property of exponents, and then we reciprocate 2 into 1 over 2 to the first power. Okay? So is 2 equal to 1 over 2? Is 2 equal to 1/2? The answer is no. So the ordered pair satisfies the first equation, but it does not satisfy the second one. So option 1 is not the answer because -1, 2 does not result in a true statement for both. Just the first one, but the second one it failed. Alright, so let's move on to option number 2. We have two functions there. Both of them are linear. So the first one is y equals x minus 1, and the second one is y equals 2x. So the question is, Does negative 1, 2 satisfy both equations? Is negative 1, 2 a solution for both equations? I mean the same thing, alright? Okay, so let's write down the ordered pair that we're working with. So we're working with negative 1, 2, and then negative 1, 2. We're going to plug in the x and the x and the y and the y. So what does that give us? We have, so 2 goes for y. 2 is 2 equal to negative 1 minus 1. What is negative 1 minus 1? Is 2 equal to negative 1 minus 1 is negative 2. Uh-oh, that is an automatic fail right there. So number 2 is not, negative 1 and 2 is not a solution for number 2 because it doesn't even satisfy the first one. So there's no need to even waste our time checking the second equation because it already failed the first one. Alright, so we keep on going until we get a situation where the ordered pair satisfies both equations. Okay, so for option 3, we have y equals x squared minus 3x minus 2. This is a quadratic trinomial. And a linear function y equals 4x plus 6. So we're going to be plugging in the solution again. The ordered pair, sorry, we don't know if it's a solution yet. We have to substitute and see if it's true or false before we know if it's a solution. Okay, so negative 1 goes into the x's, bam, bam, and then 2 goes into the y, right there. Same here, so 2 goes into the y, and then the x goes there. So we're going to substitute and see if we end up with a true statement. For the first one, we have, is 2 equal to negative 1 squared minus 3 times negative 1 minus 2, is it? Simplify using the order of operations. So if you square negative 1, you get 1. Minus times minus is a plus. Plus 3 minus 2 is 2 equal to 1 plus 3 is 4. 4 minus 2 is 2. Is 2 equal to 2? Absolutely. The first one is a check. We have to proceed to check the second one. Alright. So if we carry out the substitution, we're going to have is 2 equal to 4 times negative 1 plus 6, is it? Is 2 equal to, now we use the order of operations, you multiply before you add or subtract, negative 4 plus 6. Is 2 equal to negative 4 plus 6 is 2. Is 2 equal to 2? Absolutely, ladies and gentlemen, we have a winner. Number 3 is good because negative 1, 2 satisfies both equations or makes both equations true upon substitution, or negative 1, 2 is a solution to both equations, so the answer is option number 3. Alright, let's take a look at question 19. In this one, we'll be assessed on how to generate a function for geometric sequences. Okay. Question 19 reads, which function could be used to represent the sequence 8, 20, 50, 125, 312.5, and on and on and on, given that a1 is equal to 8. a1 is the first term, okay? Alright, before we get started, let's go over the formulas for the arithmetic and geometric series functions. Alright, so let's write this down. Formulas. For the geometric series, you know, we can write this using a recursive definition or just a function. In this case, we're using a function. So a of n, a as a function of n, is normally given by the common ratio multiplied by the term before a, the term before an minus 1. Okay? So if you multiply a common ratio by a term, that gives you the next term. Alright, so the term before an is an minus 1. Now how about an arithmetic function scenario? Arithmetic. So for arithmetic, an is basically the term, the common difference plus the term before. Alright, so you see the difference here? For geometric, you're multiplying by r, which is known as the common ratio. For arithmetic, you are adding d, which is known as the common difference. All right, so that's the difference here. So another thing to keep in mind is that the common ratio for geometric sequences is a term divided by the term before it. So let's just use concrete examples. A1 over, common ratio is A2, a term divided by the term before it, A over A1, or A3 over A2, or AN divided by AN minus 1. Alright, and then for the common difference, it's basically the term minus the term before it. Okay, A2 minus A1, or A3 minus A2, or AN minus AN minus 1. Alright, so that's that. Now let's look at what we have here. The question is this sequence geometric or is it an arithmetic sequence? Alright, so all we just have to do is see if we have a common ratio or a common difference, then we'll know for a certainty if it's arithmetic or not, or geometric. Alright, so we're going to start by testing it to see if it's arithmetic. So arithmetic test, we're looking for a common difference. Alright, so first one, D1, difference 1, we're going to subtract the first two, 20 minus 8. What is 20 minus 8? That's 12. Looking good. Alright, so difference 2, we're going to take the next two terms, 50 minus 8. No, sorry, 50 minus 20. 50 minus 20 is 30. Ladies and gentlemen, the difference are not common. Since the difference are not common, this sequence has failed the arithmetic sequence test. Okay, so this sequence is not arithmetic for sure. It's not arithmetic. Alright, so we automatically know that it should be geometric, but let's not just make any assumptions. Let's test it and see if it's geometric. Alright, so for arithmetic tests we're subtracting. Guess what we are going to do for the geometric? We're going to be dividing. Okay, alright, let's do it. Alright, so let's look for the common ratios to see if they are common, to find the ratios to see if they're common. So for the first ratio, R1, we're going to divide 20 by 8. You could do that with your calculator. So 20 divided by 8, you could divide by 4, so you have 5 over 2, which is 2.5. And then ratio 2, divide 50 by 20. 50 divided by 20, that's another 2.5. Ladies and gentlemen, it looks like we have a winner. Let's just do one more just to make sure. Okay, 125 divided by 50. Alright, let's use our calculator to check this out. So what is 125 divided by 50? 2.5. So what does this tell us? It tells us that this sequence is geometric because we're multiplying by the same constant every time. Multiply by 2.5 and multiply by 2. So when you multiply by the same number every single time, your sequence is geometric. Okay, alright, so we're going to be using this formula right here to solve the problem. All we need is the common ratio. An and an minus a sub n minus 1 are variables, so we'll leave those alone. Oh, wait a minute, we know what a1 is, right? Let's see, we're going to be using it here. No, we don't need a1. Okay, so for the geometric series formula, let's just rewrite the formula here so we can have a guide. We're using a sub n. A term is equal to the common ratio multiplied by the term before that term. Alright, we know from our computation here to the left that the common ratio is 2.5. So all we're going to do is take 2.5 and plug it into the common ratio spot in the formula, and then we're going to get an is equal to 2.5 multiplied by a sub n minus 1. The answer to question number 19 is option number 2. Alrighty, let's take a look at question number 20. In question number 20, we're going to be assessed on how to solve literal equations or formulas in terms of specified variables. Okay, so let's take a look at question 20. It reads, the formula for electrical power P is P equals I square R, where I is current and R is resistance. The formula for I in terms of P and R is, so what on earth does this mean? Formula for I in terms of P and R. What this statement is telling you to do is simply solve for or isolate I. So for I or isolate I. When you have I isolated, you're going to have the other variables, namely R and P, on the other side. That basically means I has been expressed in terms of P and R. Alright, so if we get if we get I isolated, we have accomplished the goal of expressing I in terms of P and R. Okay, so we have the equation P equals I square R. So the goal here is to solve for I. Okay, alright. So before we get started solving for I in this equation, let's do a real quick review of our inverse operations. Okay, let's do that. Alright, so review on inverses. You have to remember the following. So recall inverses. So the whole idea of inverses involves undoing an operation. If you want to isolate a variable, you have to break its relationship with other variables or constants around it. So you need to use the appropriate inverse operation to undo the existing operation that you have. For example, if you have multiply, what can undo multiplication? The inverse or opposite of multiplication is division. How about addition? If you want to undo addition, you use subtraction, and vice versa. To undo subtraction, you add. How about a quantity squared? The inverse of square is square root. So if you want to undo square, you take the root, square root. And if you want to undo square root, you take the square. Alright, so let's keep that in mind. Now for P equals I square R, we're going to isolate R in two steps. Do you see what the two steps are? The first step is to get rid of R, and then the second step is to get rid of the square. The relationship between I square and R is multiplicative. What is the inverse of multiply? Divide. So to get rid of R, we're going to use inverse operation. We're going to divide both sides of the equation by R. Okay? So see what happens here. These two divide each other out, and we have P divided by R is equal to I square. Alright, so now using the reflexive property of equality, we can rewrite this equation as I square equals P over R. Now the final move or step is to eliminate that square. What is the opposite of square? The opposite of square is square root. So to undo this square, we're going to take the square root of both sides of the equation, and that is going to yield I equals the square root of P over R. Okay, because the square and the square root cancel each other out since you're inverses. That's what inverses do. So expressing I in terms of P and R is I equals the square root of P over R. The answer to question number 20 is option number 2.